Um, Hi everyone. So today I'll be talking about one of the projects we worked on. I and my team called ONA. The concept of this project was we wanted to build something for a very small subset of users, people with low vision and visually impaired. The goal was to build out a system that could help them navigate their environments more confidently. And we tried to do this in different ways, and I'll show you guys a demo of what we ended up with. It's not a concrete solution right now, but I would say we've learned a lot while building this, and we've been able to accomplish the demo I'm going to show you. So again, just like my last presentation and demo, I'm going to wing this, and whatever I don't remember, or whatever concept I don't fully explain better, I'll ask my companion here. Let me just open a new tab. ONA, give me a sec. I think this is this. Okay. So you me ask me I will answer. Let's see if it's for one details. Um, okay, so I'll be presenting ONA. This was a capstone project we worked on last year for my final semester back at Fanshawe. We worked on, like I said, the objects navigation assistant. It was a capstone proposal. We worked on for safety purposes, and it works from capstone to auditable safety aware perception system. Yeah, and this video is going to be quite long, so I would suggest if you're really vast and you don't have the patience for it, you might have to just skip down to the demo, because I will try to audit the video and put on the description. There will be a place where I'll show you how the demo starts, so you can just skip to that point and watch the demo, what it's about. But for now, I'll just walk through every step of the project, what we did and what we ended up with right now as of the current date of this recording. First, ONA. ONA today is an adaptive system that works with different components of computer vision. We have the adaptive detector, HSC, filtering, depth and geometry, temporary persistence, urgency, friend recognition, announcement governance, and audio loss diagnostics. For FriendNet, if you watch my other video, you know what FriendNet is, and I'll let you know how FriendNet came to play in this full-on project. The goal for ONA was to detect, adapt, trust, and explain why you're telling us to move this way. And this project went in depth. We didn't just bring a couple of companies in and make it what it is right now. We did some form of research and development on our end and tried to find the right companies that fit into each other. And we worked with a latency budget to make sure that our latency doesn't go above a certain latency budget we have. Yeah. So the original proposal for our project was, like I said, we wanted to have an obstacle and hazard detection, recognize familiar faces, scene description. We wanted our users to know that if you're in a particular place or model or product will be able to tell you that this is where you are and let you know people that are around you that you're familiar with. We wanted OCR and text reading, immediate spoken feedback, eventual wearable. At the end of the day, we wanted to have something like a meta glasses that our users could wear and they could know their environment and their surroundings. So that was the initial proposal. Then we went on to do some research and ambition. Like I told you, we didn't just bring up random components and join it together. We had to do proper research, understand what would work. We use custom detector as YOLO, custom face model as FaceNet systems, custom captioning as Blip. That was the ambition. Then what we stayed and what's left. We deepened our real-time perception system, made FriendNet better, made FriendNet better, did some model benchmarking, scene filtering, adaptive orchestration, and safety diagnostics. And we didn't use the OCR or custom captioning in the current product we have right now. FriendNet. In my last video, I talked about FriendNet, how I what one of the projects I worked on back at Fanshawe, and I talked about how I built it from the ground up. I collected videos from my friends, extracted them into frames, and trained my model on it, and did a model benchmarking across Clip, ResNet 50, and my own custom CNN model. I also did a demo on that video, my last YouTube video, to let you guys know the performance of my model across the across Clip and ResNet. Anyway, so I went on to make FriendNet even more better for ONA because FriendNet, like I told you guys in the last video, it was just a base version of FriendNet. It wasn't as good, but it was a good enough model. But the next, I moved towards making FriendNet better because my last project for FriendNet was a classifier. Right now, I'm making it into the last layer of my FriendNet model became a vector dimension embedding. So what this means is unlike the last FriendNet model that did softmax classifier, I extracted the vector embeddings for each image or each frame or each class. So what I did with the vector embedding, I used it with Facebook AI and the fast vector. Wait, hold on. What is the full meaning of fast and how does network it? Yeah, Facebook AI similarity search. InfraNet fast as a system embedding engine. Like I told you, this current model of FriendNet I built, instead of having to be a classifier, it extracts and brings out vector embeddings, 512 dimension of vector embeddings. So the flow is Retina crops and detects the face, and FriendNet processes the face using ResNet based network because it was built my my backbone for my backbone for FriendNet is ResNet 50, and FriendNet converts the face into 512 dimensional embedding, a micro representation of the person's face, and the embed is normalized and sent to FAST. And FAST searches across the enrolled face and returns the closest match. This is like RAGs, present day RAGs, and yeah, this is the same algorithm RAGs use. You can either use the FAST or use PG, vector. Yeah, there are a couple of ways you could do. So conceptually, it's camera face, retina crop, friends, embedding, file similarity search, top match similarity score, threshold and gap, and quiz detected unknown face. So you see all this in play in the demo. Anyway, so I improved FriendNet, used retina crop face. Last time I didn't use retina. I just trained my model without having to crop and detect the faces, train evaluation splits, and yeah, also this time I extracted video clips from the videos. I didn't just bring out frames. I trained two models, an image model and a video model. Remember I told you image models uses 2D dimensions for CNN and video models uses 3D. Yeah, this is what I did. Use arc phase and cosine similarities matching. Cosine similarity is for the vector search on the vector database, which is FAS, and arc phase laws. If I'm correct, arc phase tries to separate unknown faces, make sure the dimensions for unknown faces are not close to the known faces. So it tries to separate them by giving them a loss. You can search that. How does arc phase work? Sorry. Infinite. Yeah. So infinite alpha trains the model to place faces from same person closer together in bed and why first another faces exactly. So how it works, when it first converts faces into 512 dimensional first also maintains a length normalized vector for each enrolled trained identity, converts its cosine similarity between face, vector, and vector, converts the face into an angle. Like I said, conceptually, it just tries to separate unknown faces and bring faces that are known together. So we got to 99.81 test accuracy, and we trained with 551,402 images and 6,433 video clips. This was the improvement. If you remember, my last training, I used just 5K images. Now I went forward to use 51,000. Next, and we just after that, I decided to even get better at Fred because after doing that with FredNet, I realized it wasn't still as good as I wanted because there were still a lot of false positives, a lot of unknown phases. I went forward to train it even harder. I used the straightened embedding head, Resonate 50, used more generalization features like Patchnum, Relu, dropouts. I told you guys what Relu was in the last video, dropouts for generation so the neurons don't what's that thing called? Don't overfit on the features and Patchnum knows what it does. Linear, the other dense layer converts this dimension to 512, which now becomes a L2 normalized embedding. Yeah, 99.98 99.98 accuracy. These are the test results. I now increased my data set from 51,000 to 120K images across 6 classes, and from 6K videos to 14K 976 clips. This was all trained on Google Colab, and I used my A100. I had to buy some extra GPUs to train this. They took some time to train FreeNet. But all in all, this helped increase my accuracy, not just on this. And I also showed a demo. I'll do a live demo of how it works, and some of my friends will be here by the time the demo starts, and you see that FriendNet could possibly recognize their faces. So integrating. So this project wasn't just a mini project, it was a capstone project. I worked with five people on my team. I was the fifth person, four other people. So there are different components in ONA. There is YOLO V8 for object detection, MiDaS for distance, and Retina Face for cropping. For it works along with FriendNet and Gemini to convert regular sentences to human sentences. So the processing pipeline is the frames are decoded into tensors. MiDaS depth to confirm how far these objects or persons are. YOLO detects hazard, check what YOLO is detecting, if it's hazard or not. If it's hazard, say the hazard. If it's not, probably a face, FriendNet kicks in. Candidate announcements, priority cooldown is so you don't have each announcement overlapping each other, and Gemini, fallback, and TTS. So the total budget was 138.8 ms, which is really good, and 5.8 FPS over full-time pipeline, all models enabled. So like I said, we had a budget of 300 MX in the beginning, and we worked with this. Mind you, all these systems are working on a MacBook Pro M4. Now imagine how good it would be if you had a better GPU or a better NVIDIA chip. So this is every single thing that happened in ONA as at 2025 December. Like I said, it was a capstone project as at 2025 December. All the budgets, we had the 300 MX budget, and we did everything with 172.4 MX. So, like I told you guys before, we didn't just want to work with what we thought was good. We had to do some research and development. Initially, when we started this project, we used V8, YOLO V8, which is one of the smallest YOLO models. And it did a good job, but it wasn't very good. You notice it was very sparse and it didn't really catch most objects. It didn't recognize most objects. So we decided to start looking for better options rather than just settling for YOLO V8. We did some comparison between YOLO V8 and faster RCNN. Um, YOLO took 2 seconds to initialize. This took 95 seconds, which is not even good. And YOLO took in first time is 20 ms, and this is even going above our total ms. This is bad. So we did some research, found out what we needed, observed FPS 30 to 60 seconds, milliseconds, I think. This is 2 to 4 seconds. This is not good. Total 200 MB, 800 MB, 400. So you see, this is not good. We tried this. We did a full-on comparison between both of them and realized YOLO is still better. Then we didn't just settle, we went forward to try different other models. So we decided to try YOLO V8, YOLO 11, YOLO 26, and the real-time detection, transformer detection, object detection model. YOLO 26, which is the present YOLO, was our best option. We tried it across YOLO V8, and realized, and you might be wondering how we came across this conclusion. We have some research and development documents. Give me a sec, ONA, no, not ONA. Give me a sec, create dev, email core, vision, ONA, ONA labs, research. Yep, these are all our documents from our research we did. You can see for YOLO evolution by ROTC. Oh, no, 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 this, not this, not this. Yes, this. I don't think we have the PDF for this. I don't think we have the PDF for this. Anyway, we have the markdown file of the reports we did, and we compared and realized YOLO 26 is way better than just other YOLO models. The conclusion here is not that YOLO is good. YOLO is good, but still it's a sparse model. It barely detects objects. Let's say we have the room is crowded with a lot of objects. YOLO might not capture the objects, and because considering the users we are targeting, they would YOLO might miss some objects which might cause an accident. So we decided to not do winner versus loss. We decided to go with YOLO and RT. RT gets more objects in dense areas. It captures most objects, but is slow and dense. Then this created a tension for SVMO. You might be wondering what SVMO is. We call it Smart Vision Model Orchestration. I will explain in this presentation and tell you and show you how it works. So we now did a different model benchmark, 11 model life benchmark. We tried with YOLO, RoboFlow, real time. These are different models we tried and compared and found, because we're trying to find the best object detection model. You might be wondering, how did we do this? How were we able to compare these models and which system did we use? We built our own ONA labs. Our own ONA lab system that had a control system where we could upload videos or run a live session across these models and get our benchmarks. Let me just show you what it looks like on our labs. Right. Give me a sec. So you see, we have a lot of models here. We have V8, we have 11, we have twin Cs, we have large, we have we have a total of 11 models here, which we tested with. Let it just load up. I'll show you what it looks like. Come on, come on, come on, come on. Uh-huh. Oops, I have to kill this. Anyway, no, not here. Safari. So this is what our ONA labs look like. We have different models you can select from. These models, you select what you want. There are different modes: detection, heat map, combined, auto, SV mode, compare. You can compare it while they're like streaming together. You can enable HCS. We have total runtime for each budget. As it's running, you're seeing the FPS inference detection configured mode. Yep, it's totally our own version of our lab, our own research and development lab. Then we have the world view. Here we upload videos we recorded of the environment. Let's say we use one of the environments we used was a grocery store. You upload the video here. Then you click analyze. As it's analyzing, it's taking screenshots, telling you what's happening. You choose the models you want to work with. You have the detection, heat map, combined the same mode, and yeah, this was our own version of this is our own version of research and development we did to have our models compare. Let me just kill this server so we don't. Oops. Okay. Back to this. So we compared across these different models and realized the 26 and RoboFlow models are much more better. Again, here is the documentation. Where is that? Like I told you, we are researching our honor labs had we built-in screenshot capabilities where as is analyzing each image, each video is taking screenshots to let us know what's happening at different times. So it's quite a capable thing. To an extent, we trust its evaluation. That's why we settled for the model we chose. So these documentations and research documents will be uploaded on my website, also on Honor's website, and to be linked on the description. You can always check this out and see and read for yourself and see what I'm talking about. So we settled for Yellow 26 and RoboFlow large model. And we did the same evaluation across what analysis. Like I told you, we can capture video. We did it across Farmboy grocery video, and every model is identical from 7,000 frames. Detection heat map, exactly the same thing I just showed you across the heat maps I showed you on the screenshots here. And again, we had detection, highest detection was this guy, most stable detection was this guy. So key comparison, you'll process quickly, but you did only 0.26 detections per frame. So you see, like I said, YOLO misses out on most detections, but the RoboFlow and real-time detection models get more scenes, which leads us back to our developed algorithm, which is SVMO. I'll show you what that is. So we realize not YOLO, the RoboFlow and the RT detection models capture a lot of objects. This is not good. It gives you a lot of objects, even the ones you don't need, keeps calling out. If I lose the system, we don't want that. So what did we do? We looked up a paper and implemented it on our system. This is HCS, hierarchical causes selection. It uses 4 functions: utility, representative, robustness, and synergy. This is the paper. Um, This is the paper that we implemented. It's from Beijing, China, University of, which school is this? Yeah, Institute of Software Academy, Institute of Software Chinese Academy of Sciences. This is where we got it from. Scene understanding is one of the core tasks in computer vision, aiming to extract semantic information from images to identify objects, things, categories, and their interrelationships. So what HCS basically means, it tries to uses the 4 functions to remove redundant objects from the screen. So for an example, let's say the RoboFlow models captures like 10 different objects in a frame. With HCS, it takes the most important ones, the ones that appear across different frames, and passes it through the pipeline. So maybe post HCS from the 10 objects might be like 6 or 7 or 4. This way it reduces the impact on our GPU, reduces the latency, and makes our system much more faster, and helps our coding algorithm so that we don't have a lot of overlapping announcements for the user. This might cause some overstimulation. So utility preserves task relevant information while staying spatially compact, reflects the wider feature distribution, not frequent objects, stays useful under perturbation like noise or visual variation. Selected regions complement rather than, yeah. These four functions was what helped build up HCS Research Foundation. So again, we didn't just plug it and hope for the best. We did some research, and this is it. Where is this? We did some comparisons with HCS and non-HCS. We realized like with HCS, it gave us better accuracy, gave us faster latency, and it was way better than just working with raw detections from the models. Again, these research documents will be uploaded, so you work with us. Then we did, what I just talked about. We did live YOLO 26, live RoboFlow, did on word analysis as well, and detection change. See, we got 5 more points from above 70% accuracies. We lost some latencies. We get some latency, but this is permittable latency because we get some points on our accuracies. And for this, we lost a little bit of latency. And if if you're working with such systems, any little latency you can lose totally helps to improve your model and helps improve your product hugely. Then we decided we have 2 models we're working with right now. We have the YOLO, we have the RoboFlow. Sorry, YOLO and RoboFlow. YOLO for sparse scenes and RoboFlow. YOLO is a bit faster and doesn't take much on our GPU because it's quite a lightweight model, and our RoboFlow model is quite heavy. So what did we decided to build up our own algorithm that switches based on how dense or sparse the scene is. So the current detector, we always start with RoboFlow model. This does the HCS filtering, spatial context, checks how dense the environment is, the entropy, how quickly it's changing, and checks even temporal, because I also trained on video models. So temporal means across different frames of place, is this object still persistent? So we did sync complexity, hysteresis. Hysteresis threshold determines how frequently the model switch, and confirm and dwell time, why is switching, and next detector. So hysteresis is a higher threshold for RoboFlow and lower threshold for YOLO. A neural zone where detector is retained and preventing single frame overlapping. So we did this and realized we got 56.1% more 6.1% more detections versus static YOLO, because here we had to involve RoboFlow. Initially, I told you we always run research on each model. So with SVMO, we realized on scenes where there are more dense places, there are more dense objects, RoboFlow will kick in and RoboFlow will detect more objects. When you go back to sparse scenes, YOLO will kick in back. So with this, we got more object detections versus just using YOLO, and we lost 30.1% latency. So that's a very huge drop. Remember, the goal was to stay below 300 mx. So these were most of the things we did to stay within our budget versus just using RF model, because using the RoboFlow model is quite heavy. So with sparse scenes, our latency budget drops on our GPU, and YOLO will kick in and make the system much faster. Again, this was since these were some good metrics we got by using SVMO. Then research continued. We tested on our main system because the goal of research and development is find out the best use case and plug it into your main system. Yeah. So we did this, and while working on our main system, we realized some inconsistencies with SVMO. Then we did some changes. Don't mind, this presentation was totally made by Claude. I just gave it a prompt and developed my good presentation for me. That's why you have this anyway. After SVM, the new target was safety, efficiency, reliability, stability, calibration, thermal variability, cognitive usability, and fault tolerance. So safety efficiency is close to hazard recorders / latency. So we noticed some inconsistencies. You might be using YOLO, or YOLO, the safety net for YOLO was a bit low and it kept switching unnecessarily. So we built some algorithms around this. So why wasn't an object announced? Why did SVM stay on YOLO? Why did HCS or cool down remove an object? Because we noticed one of the tests we did, I remember, was we are doing a demo across a car. The vehicle was quite close. No, the vehicle was far, but YOLO never passed the vehicle down the downstream to announce or even see the objects entirely. So this was bad. Imagine the vehicle was actually close. This would have caused an accident. So yeah, so why was a distant calibrate very far, very close? Why did Fresnel return wrong identity? Why was face processing skipped or to protect latency? So before it was data output, hazard plus depth was hazard label, cooldown logic speech. Now after this, we did raw evidence, we audited the HCS and changed the algorithm a bit, the temporal persistency. So like across frames, is this object still appearing before you speak? Then we did depth plus geometry urgency. So based on where the objects appear on this frame, we determine how close or how far it is. FriendNet evidence. FriendNet algorithm, it checks, like I remember I told you, FriendNet was built to do some similarity search across the database, the FCS database from the last detection head, where we extract some extract the vector dimensions. So we usually, the algorithm for FriendNet is we compare across 20 candidates to be sure that it's the right phase that's been announced. So we have an evidence, announcement block, announcement plus block reason. So if announcement is blocked, we have to know why it's blocked. The SVM intensity, probe, and switch state, and diagnosis report. All of this will be seen in our demo. You see how the entire pipeline works from top to bottom. And so these are the new things we introduced post SVMO: dense scene density, dense probe, hazard urgency, temporary persistent announcement, governance, fairness observability. So for scene density, normalized detections over megapixel plus bounding box coverage, not object counts. So dense group is periodic check is sparse scenes with strong observers, so everyone can find its way back. Because we noticed at some points, YOLO got stuck, you can see it um, got stuck and was not moving back to RoboFlow even on dead scenes. So it developed an algorithm that checks, kicks in RoboFlow mode, look around for some time. If it's dense, then RoboFlow stays. It works together with temporal persistence, so it checks across different frames, then RoboFlow stays. Then hazard urgency, we use depth. Depth from MiDaS is not evidence of authority. We combine it with bounding box geometry, path overlap, class severity, temporary trend before any emergency warning. Like I said, we added some observability from friend and some. I also noticed for announcement governance, we noticed since we're starting a TurboFlow model, once the demo starts, it starts spitting out objects immediately. This is not good because it could overlap. Some objects are overlapping and it could cause from some overstimulation. So we introduce explicit load reasons, low urgency, HCS, cooldown, frame priority, or geometry denied emergency. Silence is now explained. So, like I said, tracks objects across frames. That's standard algorithm. Introduce temporary persistence. This is not like This is not the real temporary persistence we have. I think the next version of ONA will be implementing a different paper we saw. This paper on memory temporary persistence. I think I read that paper like 2 months ago. Not deaf documents, personal study paper, no vision. I think this might be the paper. No, not this. See, aha, seeing aware optimization for streaming video creation on the. So, if I remember correctly, this paper was about understanding scenes and storing some scene based on time segments. So, yeah, if I'm not wrong, so the model, the paper tries to ask some questions based on the scenes. Is this? I'm not sure, but we'll be implementing this in the next few updates for ONA. And report viewer, we see after a quick demo, we see how report viewer works, what some of the updates we did, and the evaluations, the metrics, and we'll see how ONA works. I think, yeah, we have some limitations. Obviously, models isn't calibrated. FreeNet needs real-world improvements. Like I said, FreeNet will be updated. We'll work on that. SVM threshold, yeah, some of the updates we need to make. And yeah, let's do some demo. Ooh. See if my servers are running. Please, 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 please. Okay. Yes, I need to use my phone for this. Um, um, so, okay, let's do this demo. Stats. So stats. No, no, no. Let me do this first. I don't want the bounding boxes to show. The bounding boxes to show. Let's increase this a bit. Okay. Hopefully the voice
Obstacles ahead, so be careful.
This is my face. Yep.
Chris is just ahead of you. Watch out for nearby obstacles.
Step outside as well.
Obstacle on your left, shift right. Caution, obstacles nearby.
So,
Caution, obstacles are nearby. Obstacle right, shift left.
in.
Obstacle left, shift right. Stop, a couch is directly ahead. Chris is nearby, on your left.
Are you sleeping? Okay. And that's the demo for right now. Stop detection. So, like I said, I'll show you how the report viewer works. So we can see the performance summary, average time, runtime diagnosis, latency normal. Here we have all the objects removed by HCS, unnecessary objects, and the switch reasons. The models that we are used, Zulu was used more times because the scenes were sparse, and RoboFlow was used to identify 74 objects. So this report really has a full diagnosis of everything that happened, why, and explains the reason. So we have announcements, face announcement, two-face announcement, object announcement, 8 runtime, average time between announcements. So some reasons why announcements were blocked: object code and object global coordinator, face global coordinator, face. So if you click this, you see what they mean. And these are the announcements that came, obstacle ahead, so be careful. Remember, we use Gemini to make this a bit, make the announcements a bit human. Watch out for obstacles ahead. So, obstacle on your left. Sorry. So, yeah, detection summary. You see all the objects that were detected and how long, what if they were announced or not, if HCS removed them or not. This is a full breakdown of all the objects that were detected. And switch events, we have like 7 switch. Yellow was used, and let's see a switch here from yellow to RF detection transformer model. Dense came because the environment became dense, it switched immediately. Um, yeah, this was these were some, what's it called? Some switches as well. Tempered resistance, you see how long some objects stayed before they announced. We have the graphs. We didn't have an error in this demo. So we can run a different demo again. Let's try something else. Start. So,
Watch out for nearby obstacles.
so Tatiana is here.
Tatiana is on her way.
See,
Watch out for nearby obstacles. Obstacle on your right, shift left.
and
Stop, a couch is directly ahead. Watch out for nearby obstacles.
so we still have quite a long way to go with ONA because you can see there's still some overlapping announcements and some announcement that took some time, which could have caused an accident. And we're still very far away from understanding our scenes and explaining some affordances across subjects. So it's still a long way to go. We've not even gone anywhere. But one of our goals would be to understand the scenes, which is the paper I presented to you previously. That will be our next improvements for ONA, using the post hoc query method to understand our scenes a bit. So it's still a far cry from the current day of computer vision problems, but this is quite an interesting research for us and something we really want to keep going and improving. And so far, I showed you guys how. Remember my last video, I talked about FredNet and told you guys some applications to it. This is one of the applications of FredNet. How FredNet was plugged into the system and it's able to recognize friends that are close. And yeah, it just added some social cues to ONA. And I think that's it for today's video and presentation. This is one of the most exciting projects I've worked on, and I'm really, really, really interested in computer vision. And let me just show you guys. This presentation is quite shitty, but let me show you, because it was done by Claude. Let me show you one of the presentations we did on our capstone, what it looked like. This is ONA's website. Oops. Hold on. Oh, think speech. So this was our 285 million people suffer from visual impairments worldwide. To bridge this gap, we engineered a new sense of sight on object navigation assistance. So our goal is to see, understand, speak. And we use object detection, FredNet, contextual reasoning, synthesizer, natural speech, and feedback. The pipeline, like I just showed you, which was our initial honor, was YOLO, detecting hazard and objects, MiDaS for depth sensing, uh, human presence detection, and here's this. Human presence detection, which was FriendNet. We also did familiar friends again, and empathic reasoning, Gemini. The last one is multilingual, and also we could have our on also features language change. It's not just English. Like I said, we have like different languages: Spanish, Mandarin, German, French, Hindi, Arabic. Yeah, and that's it for today. Thank you guys, and see you on my next project presentation.